Let's now start our discussion of translation. Let us now introduce the very important concept of translation or spatial displacement. Okay, so if you have an object, we could simply translate it in space. So how do we describe such things in quantum mechanics? So how do we translate states, basically? What happens to states when we translate them, right? How do we describe such things? These are the things we are trying to understand in this session. So let us start with a simple case, all right? Let's take a state that is well localized around x vector prime, all right? This is a position x vector prime. So we are talking about a special state which is localized around x vector prime. Okay, then we can move on to general states. So we are talking about spatial translation. So it's easier to start with a state which is localized in space, Let us consider an operation that changes this state into another well localized state. Okay, this is translation. So we have got a localized state around this point. We need to translate to another another well localized state around another point. Okay, so both are localized states, which means that they don't have much spread over the position space. Okay, and then we translate the system to another point. Right, so the system after translation, before translation it was localized around this point, after translation it's localized around a different point. Okay, so this is what's happening. So let us consider an operation that changes this state into another well localized state, this time around x vector prime plus dx vector prime, with everything else unchanged. So we are simply translating the state in space. Okay, we are not changing anything else. Right, if there are some vectors associated with the system like spin, etc., we don't change any of this. This is a simple translation in space. Okay, and we are discussing the translation of a localized state. Let's represent this localized state by ket x prime. Right, so this represents a state that is localized at x prime, at the position x prime. We earlier mentioned that such states do not exist in practice. Okay, but it's still useful. All right, we can still use them in our mathematical formulation. So let's say that we have got a state ket x prime, which is localized at the point x prime, and then another state, right, ket x prime plus dx prime, which is localized at the point x prime plus dx prime. Right, if you are talking about 3 dimensions, we should write this as x vector prime and x vector prime plus dx vector prime. Right, if you are talking about 3 dimensions, 3-dimensional translations. Okay, so this is a state that's localized at a point denoted by x vector prime, and this is a state that's localized at a slightly different point, x vector prime plus dx vector prime. These are two kets, and we know that two kets are related by some operator. Right, so let's define the translation operator in this manner. All right, so what's the operator that takes you from this ket to this ket? This operator shall be called the translation operator. Okay, so the job is done by, this is j written in a funny manner, so we'll try to write this. So this is j, cursive j, or curly j, capital J. Okay, the translation operator. Right, so we define the translation operator j of dx vector prime in this way. It's defined like this: j of dx vector prime, the operator acting on ket x vector prime, gives you ket x vector prime plus dx vector prime. Right, so this is the operator. This is defined as the operator that takes your state from ket x vector prime to ket x vector prime plus dx vector prime. Right. Now, when we define like this, there is still a phase factor to be fixed. We'll fix this to unity by convention. We'll fix this phase factor to unity by convention. All right. Now, notice that the right-hand side is again a position eigenket. This is again a position eigenket, but this time with eigenvalue x vector prime plus dx vector prime. The eigenvalue has changed. Obviously, ket x vector prime is not an eigenket of the infinitesimal translation operator. All right, so this is an infinitesimal displacement, an infinitesimal translation. Okay, so this we call as an infinitesimal translation operator. All right, so and we see that the infinitesimal translation operator acting on ket x vector prime gives you another ket. Right, so clearly this is not an eigenvalue equation. This means that ket x vector prime is not an eigenket of the infinitesimal translation operator. Now we have defined the infinitesimal translation operator by its action on a position eigenkette. Okay, it's defined like this. This is equal to get x vector prime plus dx vector prime. All right. Now we can check the action of this infinitesimal translation operator on an arbitrary ket, all right, some state ket alpha. How do we know this? Because since we know this definition, since we know the definition in terms of the position eigenkets, we can expand this ket alpha in terms of the position eigenkets, right? Because the position eigenkets forms a basis. So that's what we do. Ket alpha, we are looking at the effect of this infinitesimal translation operator on ket alpha. So let's say that ket alpha goes to j of dx vector prime acting on ket alpha. That's equal to j of dx vector prime acting on, here we have expanded ket alpha in terms of the position eigenkets. These are the expansion coefficients or the wave functions. These are the position eigenkets, and we are integrating over all space. Okay. Now this dx vector prime correspond to an infinitesimal translation. All right, it's a small displacement. It's a small translation in space. So I can take this inside. All right, so this j of dx vector prime acts on ket x vector prime, and it takes it to ket x vector prime plus dx vector prime. Right, because this is the basic definition. This is how this operator is defined. The action of j of dx vector prime on ket x vector prime is defined, and it takes it to ket x vector prime plus dx vector prime. Right? You can think of this dx vector prime as a small number, an infinitesimal number with the dimensions of length. Right? Okay, so we have this action of the infinitesimal translation operator on ket alpha. Right? So it takes ket alpha to a state which is written like this. Now, since this integration is over all space, all right, we are talking about the entire three-dimensional space. This is a volume integral. We are integrating this over all space. Okay. So instead of using x vector prime as the variable of integration, we could as well use x vector prime minus dx vector prime. Because in any case, we are integrating over the entire space, right? You could use x integrate over d cube x. You could integrate over x vector prime or x vector prime minus dx vector prime, right? Whichever variable you use, you are still covering the entire three-dimensional space. So this doesn't matter, right? But if you make the substitution into this integral, it looks slightly different, right? This part does not change. You'll have d cube x prime, right? And this becomes simply x vector prime, right? This part becomes simply x vector prime, right? So here it does not change. This becomes simply x vector prime, and this becomes x vector prime minus dx vector prime, right? So we have made this substitution everywhere, right? So what we have done here is that we have taken the right hand side here, okay, and written it as, this is the right hand side. We have made the substitution x vector prime goes to x vector prime minus dx vector prime, right? We made the substitution, right? Nothing else changes because still you are integrating over the entire three-dimensional space, whether you are using x vector prime or x vector prime minus dx vector prime as the integration variable. All right. So this becomes integral d cube x prime ket x prime bar x prime minus dx prime ket alpha. Okay, because the integration is over all space and x vector prime is just an integration variable. All right. So this is what we have. We had ket alpha, which is expanded in terms of the position eigenkets, x vector prime. Okay, these are the wave function. This is the wave function of the initial state. Okay. Now let's look at the translated state. The translated state is given by the action of j of dx vector prime on ket alpha. We found that, and we saw that we could write this as d cube x prime. This is ket x prime. Again, we are expanding the translated state in the position eigenkets, and here we have got x vector prime minus dx vector prime ket alpha. Right? So we see that the wave function of the initial state, we look at, okay, how the wave function changes, right? This is the wave function of the initial state. We get the wave function of the translated state by substituting, right, or by replacing this x vector prime here by x vector prime minus dx vector prime. Okay, so that's what we say here. This shows that the wave function of the translated state is obtained by substituting x vector prime minus dx vector prime for x vector prime in the initial wave function. Okay. Now, what does it say about the probabilities? What does it say about the probabilities? Okay. So in this case, we say that the probability of measuring a particle in a small volume d cube x prime around the point x prime, right, around the position x prime. This is given by bra x prime, bra x vector prime, get alpha modulus squared multiplied by d cube x prime. What is this? This is the probability of measuring the particle or finding the particle, let's say, it is around or in a small volume d cube x prime around the point x prime. So we are taking the point x prime and we are looking at the probability of measuring the particle in a small volume around this point x prime. Okay. All right. Here also you could ask the same question. What's the probability of finding the particle in a small volume d cube x prime around x prime? Right. That's answered. That answer can be obtained from this wave function. Right. It says that the corresponding probability here is given by modulus square of bra x vector prime minus dx vector prime get alpha and then d cube x prime. Okay, so here this is the probability of measuring a particle in a small volume d cube x prime around x prime or around the point x vector prime. Okay, this is of the initial state, right? But the translated state, if you look at the translated state, the probability for measuring the particle around x prime, right, or in a small volume d cube x prime around the point x vector prime is given by this. Okay, all right. Now I want you to look at this and understand what it actually says. Okay, I leave it as an exercise for you. Look at these two probabilities and what does it actually say? What does it actually say? Okay, so I leave it as an exercise to interpret this. Interpret it. Okay. There's an equivalent approach to translation that is often treated in the literature. So in that approach, instead of considering an infinitesimal translation of the physical system itself, we consider a change in the coordinate system being used such that the origin is shifted in the opposite direction. Okay, so both these are equivalent ways of describing the same thing, all right? I think we have already discussed this in classical mechanics. If you have a system like this, you could translate the system by an amount dx vector prime, all right? Or equivalently, the same translation can be described by a translation of the coordinate system in the opposite direction minus dx vector prime. Okay, the effect would be the same, all right, for all mathematical purposes. So I think we have discussed this, right? But if we start with one approach, it's important to stick with the same approach. We shouldn't mix them up. Physically, this alternative approach, in this alternative approach, we are asking how the same state get would look to another observer whose coordinate system is shifted by minus dx vector prime. Okay, this is not the approach that we are following, at least in this chapter, right? And it's important not to mix up the two approaches. Right? Let's now talk about the properties of the infinitesimal translation operator. All right. The first property we demand is the unitarity property imposed by probability conservation. Right? So the idea is this: suppose we have a system, right, a quantum mechanical system. By simply translating it in space, right, by simply translating it in space, we don't want the probabilities to change. Okay, the physics does not change by simply translating the system in space. Okay, so we need the probabilities to be conserved. All right. So one way of stating this is that if initially it's normalized to 1, all right, the translated states also should be normalized to 1. Translated states also should be normalized to 1. Right? Now this property is famously satisfied by unitary transformation. Unitary transformations are important in quantum mechanics. Okay, suppose a state get alpha is translated to u get alpha. It could be any unitary transformation, right? It could be any unitary transformation. So then bra alpha would go to bra alpha u dagger, right? What's inner product what's inner product of this transformed states? If you look at this inner products, you get bra alpha u dagger u get alpha, but u dagger u is the unit operator, so we get this is equal to bra alpha get alpha. Okay, So we see that the normalization is preserved under general in any unitary transformation. So any unitary transformation preserves the normalization. Okay, in other words, okay, we can say that in general, scalar products are preserved under unitary transformations, all right? Or inner products. I think we are using the term inner product, so we should say inner products are preserved under unitary transformations. All right. This also means that distinctions are preserved. If you have got two kets which are orthogonal to each other, they will remain orthogonal to each other under unitary transformations. Okay. So if two states are distinct, they will remain distinct. They will remain distinct. Okay. Now we have got analogous things in the three-dimensional Euclidean vector space. We know that if you have two vectors, and you rotate the vector, the length of the vector does not change. The length of the vector does not change. Right? Inner products do not change. Or scalar product between vectors do not change under rotations. Right? These things we have already seen. Okay, and this condition actually puts some constraints on the kind of transformations that we can talk about. All right. So here, it is reasonable to require that ket alpha is normalized to unity. Okay. If the ket alpha is normalized to unity, the translated ket is also normalized to unity. Okay. So this is exactly what we said here. Right? We demand that if ket alpha is normalized to unity, then the translated ket is also normalized to unity. So this is what we want. We want bracket alpha alpha is equal to the inner product between the translated states. All right. So this is the translated ket. This is the corresponding translated bra. So this is the condition that we demand. We are demanding this. We are demanding that this does not change, or inner products in general are preserved. Okay. Now, if this demand, we see that this demand is satisfied if j dagger j is the unit operator. Okay. So this condition is guaranteed by demanding that the infinitesimal translation be unitary. That's j dagger of dx vector prime multiplied by j of dx vector prime equal to 1. All right. So this is an important property. This translation operator, the infinitesimal translation operator, has to be unitary. It has to be unitary. Okay. Now, quite generally, the norm of a ket is preserved under unitary transformations, right? So even if it's not normalized to 1, whatever the norm of the ket is, it is preserved under unitary transformations. Okay. For the second property, suppose we consider two successive infinitesimal translations, first by dx vector prime and subsequently by dx vector double prime, where dx vector prime and dx vector double prime need not be in the same direction. We are talking about vectors, so we can talk about first a translation in this direction and then a translation in this direction. Okay. Now, in this case, we expect that the net result to be just a single translation operation by the vector sum dx vector prime plus dx vector double prime. Okay. What we expect is a single translation. Right? This can be represented by a single translation. Okay. For example, suppose first I make a translation along this direction, all right, and then I make a translation along this direction. Right? Let's say that this is dx vector prime and this is dx vector double prime. We expect that the final translation, or it can be written as a single translation, which is dx vector prime plus dx vector double prime. All right, now it's logical to demand that this condition is satisfied. We expect the net result to be just a single translation operation, okay, by the vector sum dx vector prime plus dx vector double prime. Okay, so we demand that this is j of dx vector prime followed by j of dx vector double prime. Right, one translation followed by another translation. Right, we expect that this can be written as a single translation. Right, or the single translation of dx vector prime plus dx vector double prime, and the corresponding operator would then be j of dx vector prime plus dx vector double prime. Okay, so we need this condition j of dx vector double prime multiplied by j of dx vector prime is equal to j of dx vector prime plus dx vector double prime. If we write this first, because if I put a state here, I want this translation to act on it first and then this translation. All right. In some cases, it might be that the order of the transformations you make doesn't matter. All right. But in general, you have to be careful of the order of transformations that you make. So it's better to what is it's better to write the first transformation, whatever it is. It could be a translation, it could be a rotation. It's better to write the first transformation on the right side, okay, because it's acting on the state, all right, and the second one to the left of it, all right. Now, the third property is this. Suppose we consider a translation in the opposite direction, all right. We expect the opposite direction translation to be the same as the inverse of the original translation. So initially, I make a translation in this direction. The inverse translation, right? The inverse translation would be to make it in this direction, all right? But the inverse translation is actually equal to translation by, let's say that this is dx vector prime, all right? The inverse translation takes you from here to here, but that's also equal to the translation by an amount minus dx vector prime. All right, so this condition can be written as j of minus dx vector prime is equal to j inverse of dx vector prime. Okay. For the fourth property, we demand that as dx vector prime tends to 0, the translation operation reduces to the identity operation. Okay, that is limit dx vector prime tends to 0, j of dx vector prime has to be equal to 1. Now, this is understandable. If I am taking dx vector prime tends to 0, that means that I am not making any translation at all. I am not moving the system at all. Okay, then the translation operator is nothing but the identity operator because you are not changing it at all. Okay. Now, there's another way of saying this, right? We are talking about infinitesimal translation operator. We are talking about an infinitesimal translation operator. Okay, so infinitesimal translation operator means you are making only a very small change, which means that it's very close to the identity operation. The infinitesimal translation operator has to be very close to the identity transformation or the identity operator. Okay, it could change infinitesimally from the identity operator. It could change infinitesimally from the identity operator. So we can have a term which is in first order in this parameter, right? In the first order, which is in the first order of this parameter dx vector prime, right? So this infinitesimal translation operator, we should be able to write it as the identity operation plus some term, some infinitesimal term, which is first order in dx vector prime. Okay. That's what we say here. The difference between j of dx vector prime and the identity operator has to be of first order in dx vector prime. Right? So when we say that we are only taking the first order terms, okay, if dx vector prime is really an infinitesimal quantity, then the higher order terms you should be able to neglect. All right. So when do we say that dx vector prime is very small? We say that dx vector prime is very small if dx vector prime square, okay, is negligible, if higher order terms are negligible. Okay, that's the reason why we say that the difference between j of dx vector prime and the identity operator has to be in first order in dx vector prime. Right? It's the same thing as saying that this translation is an infinitesimal translation. Right? Let's now demonstrate that if we take the infinitesimal translation operator to be j of dx vector prime is equal to 1 minus I k vector dot dx vector prime, right? Where all the components of k vector, kx, ky, and kz are Hermitian operators, then all the properties listed above are satisfied. So we had a few properties, all right? Importantly, unitarity, and then the other properties. All right. Now we'll show that we can define the infinitesimal translation operator in this manner. All right. You see that it changes only infinitesimally from the identity operator, just as we said in the previous slide. Okay, this changes only infinitesimally from the identity operator. All right. So we can show that if we define the infinitesimal translation operator like this, in such a way that this k vector, this is an operator which is Hermitian. This is a Hermitian operator, which means that each of its components is Hermitian. All right, each of its components is Hermitian. All right, so where the components of k vector, kx, ky, and kz are Hermitian operators, then all the properties listed are satisfied. Okay, now we'll get used to this kind of construction, right? But let's now check first. Right, so we have written down an operator that changes only infinitesimally from the identity operator. Let's check the unitarity. Let's first check for unitarity. All right. So let's find j dagger dx vector prime, j of dx vector prime. All right. So if you define this as j, then what's j dagger? J dagger is identity operator plus this minus I will become plus I, k will become k dagger. Right? That's why I've written I k dagger dot dx vector prime. This is j dagger if I define j like this. All right, and I write down j here. This is 1 minus I k dot dx vector prime. All right. Now we said that this dx vector prime is an infinitesimal quantity, so uh, we'll neglect all higher order terms. All right. Whenever such multiplications appears, we'll neglect all higher order terms in dx vector prime. Right. We'll only retain up to the first order terms in dx vector prime. So this is, if I make this multiplication, right, this is 1, right, minus ik vector dot dx vector prime, all right, plus ik vector dot dx vector prime. There's one more term. It's a dagger here, right? So this is 1 minus ik vector dot dx vector prime plus ik dagger, okay, plus ik vector dagger dot dx vector prime, all right? There's one more term, plus I minus I, that's 1, and this k dagger k dx vector prime dx vector prime, but this is second order. All right, if you take this multiplication, this is of the order of dx vector prime square. All right, so we retain only the first order terms. This means that this can be written as 1 minus, this minus can be taken outside, minus k vector minus k dagger dot dx vector prime, right? K vector minus k vector dagger dx vector prime. All right, now if this has to be unitary, if you are talking about a unitary transformation, a unitary operator, this is unitary if k minus k dagger is 0, or in other words, if k vector is equal to k vector dagger. Right? So we can write the unitary operator like this, an infinitesimal unitary transformation in this form, provided this k vector are Hermitian operators, all right, or the components of k vector are Hermitian. All right, so if k vector is equal to k dagger, we get this equal to 1. So we see that the first property is clearly satisfied. All right, the unitarity of j of dx vector prime is satisfied, where the terms of second order in dx vector prime have been ignored for an infinitesimal translation. Okay, let's now check the second property. All right, so we start with j of dx vector prime. Right, the action of j of dx vector prime followed by the action of j of dx vector double prime. Right, we know that this has to be, this we should be able to write as j of dx vector prime plus dx vector double prime. Right, this is one infinitesimal translation followed by another infinitesimal translation, so you can write it as one translation. That's the idea. Okay, now again, it's easy to check. You just write down the form of infinitesimal translation operator that we wrote down. This is 1 minus ik vector dot dx vector double prime multiplied by 1 minus ik vector dot dx vector double prime. And in multiplying, we neglect any higher order terms in dx vector prime. All right, so this becomes 1 minus ik vector dot dx vector prime plus dx vector double prime. Right, now what is this? If this is j, this is j of dx vector double prime, then this is j of dx vector prime plus dx vector double prime. Okay, now I leave it as an exercise to check the third and the fourth properties. All right, check third and fourth properties. All right, now the third property I think was this: if I take j of minus dx vector prime, I should get j inverse of dx vector prime. All right, you can check this. How do you do that? You take j of minus dx vector prime based on the definition, based on this definition, all right, and show that j acting on j multiplied by j of minus dx vector prime gives you the identity operator. That's how you check this. Okay, repeat. What we need to prove for the third property is this: j of minus dx vector prime is actually equal to j inverse of dx vector prime. How do I check this? How do you check this? Right? You start with j of minus dx vector prime. That would be 1 plus, right, let me write down here, j of minus dx vector prime would be equal to 1 plus ik vector dot dx vector double prime. All right. Now, if this has to be equal to j inverse of dx vector prime, that means that j multiplied by j of dx vector prime multiplied by j of minus dx vector prime has to be equal to the identity operator. Well, this is what you need to check. That's it. All right. So please check that. Again, when you make this multiplication, you can neglect the higher order terms. Now the fourth property was that if I take dx vector prime tends to 0, I'll get the identity operator. That's clearly satisfied. That's exactly how I constructed. That's exactly how we constructed this operator in the first place. Okay, this is an operator that changes only infinitesimally from the identity transformation. Okay, So now we can accept this definition, right? We can accept J of dx vector prime can be written as, the infinitesimal translation operator can be written as 1 minus I k vector dot dx vector prime, right? Now if you accept this definition, we are in a position to derive an extremely fundamental relation between k vector and the x vector operator, right? We'll derive an important relation between k vector and x vector operators. Okay. Of course, we are trying to find the commutator between the components of k vector and the components of x vector. Right? We know that x vector is a vector operator. We can write its components as xi. K vector is also a vector operator. It has three components which we can denote as ki. All right. Now we are looking for the commutation relations between these components. So we want to find ki with kj, xi with kj. What is this? Right? This is what we are trying to find. So we can find this because we know the action of an infinitesimal translation operator on a position eigenket. We also know the action of the position operator on a position eigenket. So we can make use of these two things to find these commutation relations. Okay. So let's first start with this. Right, we have got a get x prime, x vector prime, first acted upon by j of dx vector prime, and then acted upon by x vector. Right? So this is the order in which we take it first. Right? First, there's this infinitesimal translation operator, and then x vector. Let's find this. All right. We know the action of j of dx vector prime on get x vector prime. This is equal to get x vector prime plus dx vector prime. Right. So this j of get x j acting on get x vector prime can be written as get x vector prime plus dx vector prime. That's infinitesimal translation operator. That's how we defined it. Okay. And then we have got this x vector here. So the x vector operator, the position operator acting on get x vector prime plus dx vector prime. What are these? These are the position eigenkets. These are the position eigenkets, and these are labeled using the position eigenvalues. Right? So this is just an eigenvalue equation for the position operator, and this gives you the eigenvalue multiplied by the same kit. Right? So if I do it in this order, first the infinitesimal translation operator, then the position operator, the result I get is x vector plus dx vector prime acting on x vector plus get x vector plus dx vector prime. Okay. Now we do it in the opposite order. Right? First, you act operator x vector on get x vector prime, and then the infinitesimal translation operator. All right, and this action I already know. X vector acting on x vector prime gives you the eigenvalue, which is denoted as x vector prime multiplied by get x vector prime. This is an eigenvalue. This eigenvalue can be taken to this side. All right, remember this is an operator and this is an eigenvalue. Okay, so this is a number. It will go here. So sorry, this is a number. It can go to the left of this operator, and you get x vector prime, a number. It's a collection of numbers basically, because we are talking about 3 dimensions. Okay, so it's x vector prime, j of dx vector prime acting on get x vector prime. What is this? This is equal to x vector prime, which is this, and we know the action of j of dx vector prime on get x vector prime, which is nothing but x vector prime plus dx vector prime. All right. So this is what we get. This is what we get if I act first the infinitesimal translation operator and then the position operator. Here, get x vector is acted upon first by the position operator and then by the infinitesimal translation operator. We see that we get different results. This means that x vector and j of dx vector prime do not commute. The order matters. All right. So let's find the commutator of x vector operator with the infinitesimal translation operator. Okay. So the commutator is found by just take this and subtract. If I write this as equation A and equation B, all right, you just find A minus B. All right. On the left hand side, I have got get x vector prime here. That's the get x vector prime. All right. And if I subtract this, I get x vector j minus j x vector. That's nothing but the commutator of x vector with j of dx vector prime. Okay. So when I subtract on the left, I get this commutator. Right. On the right, I get, you see that this x vector prime multiplied by x vector prime plus dx vector prime. Okay. Sorry, x vector prime multiplied by get x vector plus get x vector prime plus dx vector prime cancels with the same thing here. right? We are left with dx vector prime multiplied by get x vector prime plus dx vector prime, right? So you just subtract and you'll get this. On the left hand side you have the commutator of x vector and j. On the right side you have got dx vector prime multiplied by get x vector prime plus dx vector prime. Right? Now we are talking about infinitesimal quantities. So we can neglect terms in second order of dx vector prime. Right? So here I've got x vector plus dx vector prime inside the get. Here I've got a dx vector prime outside. Okay. So we say that up to first order in dx vector prime, if I'm retaining only terms up to first order in dx vector prime, this can be approximated as dx vector prime multiplied by get x vector prime. Right? Hope this is clear. Okay. The error made in writing the last part is of the second order in dx vector prime. Right? There's actually obviously an error in writing this out, but this error is in second order. Okay, this error is of second order in dx vector prime. So it's of the order dx vector prime square. Okay. All right. Now this is what we have. Commutator of x vector with j of dx vector prime acting on get x vector prime is equal to dx vector prime multiplied by get x vector prime. Okay. Now this is a position eigenket. We did not assume anything specially about this particular get, right? So this is true for any position eigenket. This is true for any position eigenket, right? And if it is true for any position eigenket, it's true for any vector. It's true also for any vector. Why? Because any vector or any get can be expanded as a linear combination of the position eigengets. Right? In other words, position eigengets form a complete set. Right? So if this is true for all position eigengets, this is also true for any vector, which means that we have a general operator relation. This means that this commutator has to be equal to dx vector prime. Right? That's why we have this here. This means that we must have an operator identity x vector. So this relation actually says something about these operators. All right, it tells us something about these operators because it's true for any get. So that's why we have this identity x vector, the commutator of x vector with j of dx vector prime is equal to dx vector prime. Okay. All right. In the next step, we can use the form of this translation operator, infinitesimal translation operator that we found. J of dx prime has to be equal to, or it can be written as 1 minus I, and we have got k vector dot dx vector prime. Right? This was the form of the infinitesimal translation operator that we motivated. Okay. Now we make use of this form in this relation. All right. So we can write this as actually this is nothing but the commutator. This is x vector multiplied by j of dx vector prime minus j of dx vector prime multiplied by x vector is equal to dx vector prime. Right? That's this relation. Right? Now I substitute this j of dx vector prime is equal to the identity operator minus I k vector to dx vector prime. Right? So let's calculate the left hand side first. I'll do it here. All right. So looking at the left hand side, this is equal to x vector multiplied by 1 minus I k vector dot dx vector prime. Okay, I've taken it in one order minus 1 minus I k vector dot dx vector prime multiplied by x vector. This is the left hand side. Okay, on the right hand side it's simply a dx vector prime. Okay, let's solve the left hand side first. So this is equal to x vector minus I x vector k vector dot dx vector prime. Okay, numbers. These operators do not do anything to numbers. So I can write it like this, all right? And here I have got minus. This is x vector minus I k vector dot dx vector prime multiplied by x vector. Okay, this is the left hand side, right? We see that this x vector here cancels with this minus x vector, and I have minus I x vector k vector dot dx vector prime. Okay, plus this minus with this minus becomes a plus. This is plus I k vector dot dx vector prime multiplied by x vector. So it's the left hand side. So this reduces to I x vector k vector dot dx vector prime plus I k vector dot dx vector prime multiplied by x vector. This is equal to dx vector prime. Okay. All right. Now we could actually multiply throughout with I. Right? We could multiply throughout by I and write it like this. We can write this as, if I multiply throughout by I, the first term becomes x vector k vector dot dx vector prime minus, okay, when I multiply by I multiplied by I becomes minus 1. That's why I have a minus 1 here, whereas I multiplied by minus I is plus 1. Right? So you get x vector k vector dot dx vector prime minus k vector dot dx vector prime and multiplied by x vector. This is equal to, since I multiplied throughout by I, we should multiply on the right hand side. So this is I multiplied by dx vector prime. Okay. All right. What we need is the commutator between components of x vector and k vector. So let's find that. Okay. So this is what we have from the previous slide. We have x vector k vector dot dx vector prime minus k vector dot dx vector prime x vector is equal to I dx vector prime. If you look at this, this is a vector equation. Right, on the left hand side we have a vector. This is not a vector, but x vector is a vector. Right, this is a scalar product of two vectors, so it's no more a vector. But this x vector is a vector. Right, here we have got I dx vector prime. That's also a vector. Okay. So when do you say that two vectors are equal? We say that two vectors are equal when all their components are equal. Okay. So this can be written in the component form like this. I take the ith component of the vector on both sides. So this can be written as xi, okay, k vector dot dx vector prime minus k vector dot dx vector prime xi. Okay, this is the ith component of the vector appearing here. Remember that this k vector dot dx vector prime does not have any index. It's a scalar product. It's an inner product. It doesn't have any index. Right? So only object with index is this x vector here. Right? So xi k vector dot dx vector prime minus k vector dot dx vector prime xi. I'm taking the ith component on both sides. So I've got this I, which is the imaginary, and dx prime I. Right? This I is the index, not imaginary. Right? This is the index. Okay. Now I can further write this as, I can use the Einstein summation convention and write this as xi remains. This k vector dot dx vector prime can be written as kj dx prime j. This can be written as kj dx prime j. Sum over j is implied. The summation over j is implied. Okay. So this will give me k1 dx1 plus k2 dx2 plus k3 dx3, which is nothing but k vector dot dx vector prime. Okay, minus, similarly I write this as kj dxj, okay, prime dx prime j, and I have got this xi here. This is equal to I dx prime I. Right, now this dx prime I can be written as dx prime j delta ij. This can be written as dx prime j delta ij. Okay, you can check if this is true. There's a sum over j. If I carry out the summation, the only term that survives is one for which j is equal to I. Right. So when I carry out the summation, I'll get back this dx prime I. Right. So now this can be written as, okay, this is xi kj. Right. This dx prime j is common now. It's an infinitesimal parameter. Right. It's a number basically with the dimensions of length. Right, so this dx prime j can be pulled out now. So I get xi kj minus kj xi, okay, multiplied by dxj prime. This is equal to I, let me write this like this, delta ij dxj prime. Okay, so here we have got dxj prime, and here also we have got dxj prime. It could be any infinitesimal displacement. Right, so it must be true that whatever appears here. Right, so on both sides of this equation, I have got dx prime j. Right, which means that this thing xi kj minus kj xi has to be equal to I delta ij, because this is true for any infinitesimal, any arbitrary infinitesimal displacement. Okay, so this means that we must have xi kj minus kj xi is equal to I delta ij. Right, in other words, this is nothing but the commutator of xi and kj. Right, the commutator of xi with kj is equal to I delta ij. Okay. All right. So again, delta ij is understood to be multiplied by the identity operator. Right. So the identity operator is everywhere, wherever we need, wherever we haven't mentioned specifically. All right. Even earlier we did not mention specifically, but you have to remember that if you have an operator equation, and on one side if you don't see an operator, there has to be an identity operator there. All right. Okay, we get this relation. Okay, this is the commutation relation that we wanted to derive. Okay. Now this means that if I take x1 with k1, I get I. If I get x1 with k2, I get 0, etc. Right? So xi with kj, the commutator of xi with kj is I delta ij. Right? In this session, we define the infinitesimal translation operator by its action on the position eigenket. Okay? We say that has to be equal to get x vector prime plus dx vector prime. Okay. And then we said that if this is a infinitesimal translation operator, it has to satisfy certain properties, like unitarity, for example. We said that it has to be unitary, and there are some other properties. Okay, we discussed these things, and we saw that if we define this I of dx vector prime as an identity operator minus I k vector dot dx vector prime, right? If I define it like this, right, as an operator that changes infinitesimally from the identity operator. So this is an operator that corresponds to a change which is infinitesimally different from the action of the identity operator, because we are talking about an infinitesimal translation operator. Right? We saw that we can define a translation operator, in the infinitesimal translation operator, in this form, and all the properties are satisfied, all the necessary properties are satisfied, provided this is a Hermitian operator. All right. Now you might wonder why I have an I here. We could simply say that this translation operator is 1 minus some j vector dot dx vector prime. Right? This could have something to do with the generator of the translation, etc. But then we'll see that if these properties have to be satisfied, j vector has to be anti-Hermitian. Right? So we put this I here, we take this I out here to make this operator a Hermitian operator. And we are more interested in Hermitian operators because observables are represented by Hermitian operators. Right? Later on, we'll see that corresponding to observables, corresponding to any observable, we can construct a unitary transformation. Right? We'll say that a Hermitian operator can be considered as a generator for a particular unitary transformation. So right, we can say that Hermitian operators are generators of unitary transformations. All right, so we want to have a Hermitian operator here. That's why we write it in this form. All right. Now we found the commutator relations x vector with, we wrote it like this, xi with kj is equal to I delta ij. All right. Now we'll soon identify, we said that we are interested in observables, we'll soon identify that this is related to the linear momentum operator in quantum mechanics. This will actually motivate why we should call this, or we should associate this with the linear momentum operator. All right. Now some of these things you might be able to make a connection with the things that you studied in classical mechanics. In classical mechanics, when you studied infinitesimal canonical transformations, you might have learned that the momentum is a generator of space translations, the Hamiltonian is a generator of time translations, and the angular momentum is generator of rotations, etc. Right? These things you have discussed, right? So similar analogous concepts can be defined in quantum mechanics also. Okay? Specifically, actually, we'll define a momentum operator to be that operator that generates the spatial translation. Right? This is the tactic that we'll be using throughout the course. We'll define an angular momentum operator as an operator that generates a rotation. Right? But we are yet to make that connection. We'll do that in the next class. Okay, thank you.